Okay, this is Unit 6b, and this goes back to something that would have been addressed in the fall. So here we're talking about drawing Lewis structures. In addition to molecular names and molecular formulas, we can represent molecules using a simple drawing known as a Lewis structure. The Lewis structure shows us really three things about a molecule. It shows us the relative location, so how they're put together, the valence electrons of each atom, and it also shows us how the atoms are bonded together. It shows their covalent bonds. There are two systems that I'm showing in this particular unit. The first system is one that I've been using for a long time, and the second one in the next video is one that I've learned more recently, and it works really well, but the first method is something that we should talk about. So step one is predict the location of atoms. So for these examples, I'm going to use ammonia, and I'll draw step-by-step pictures. So predict the location of the atoms. Usually, the atom in the middle is closer to the left side of the periodic table. Usually. Now, this one's not a good example in this respect because hydrogen is at the far end of the periodic table, the far left side, and hydrogen can't be in the middle. It just doesn't have enough places to hold electrons. It's too small. The atom in the middle also tends to be the atom listed first in the name and in the formula. So in this case, that is true. So hydrogen is an exception to a lot of these, especially with ones like water. So I've got nitrogen and I've got 3 hydrogens. I'm just going to place them around it. The exact placement right now is not important. Number 2, count the number of electrons available for bonding. This is the total number of valence electrons from all the atoms in the molecule. So for nitrogen, it's in group 15. That tells me it has 5 valence electrons. And there's 1 atom of nitrogen. And so there's 5 electrons. Then hydrogen. Each hydrogen has 1 valence electron, and there are 3 hydrogens. So there's 3 electrons. And so we have a total of 8 valence electrons to be used. In step 3, determine the number of electron pairs. So we're going to divide the total valence electrons by 2. So I'm going to take this number and divide it by 2, and that tells me 4 pairs of electrons. So for step 4, I'm going back to the drawing that I made. So I already predicted the location. So I'm going to place a single bond between the central atom, that's the nitrogen in this case, and each of the terminal atoms. In this case, that's the hydrogen. They're the ones on the outside. Here's a single bond, here's a single bond, here's a single bond. Each single bond is 1 shared pair of electrons. And I'm going to keep track over here as I do this. So I've used 3, and so I have 1 pair of electrons left. And this is step 5. So determine the number of electron pairs remaining. Subtract the number of pairs used in step 4. That was these ones. From the pairs found in step 3. That was these ones. The remaining pairs will be lone pairs or possibly double or triple bonds. Depends on the molecule. In this case, these are going to be lone pairs. It says place the lone pairs around each terminal atom to satisfy the octet rule. But if we look at each of the terminal atoms, they're hydrogen. Hydrogen, to satisfy the octet rule, actually only needs 2 electrons. So this one, which is covalently bonded, thinks it has 2 electrons. This one thinks it has 2, this one thinks it has 2. So all of the hydrogens satisfy that version of the octet rule that applies to hydrogen. So what do? Assign remaining pairs to the central atom. So I'm going to place them here on the central atom. In step 6, I want to see, does the central atom obey the octet rule? If the central atom is surrounded by 4 electron pairs, that's good, we're done. If not, there are some other steps that has to happen. Looking at this one, we have 1, 2, 3, 4 pairs surrounding the central atom. And so this one is our completed Lewis structure. Here are some elements that tend to form double bonds: carbon, nitrogen, oxygen, sulfur. It happens often enough. Then at the bottom of this page, you may notice some family trends when you draw Lewis structures. So elements in group 17 form 1 single bond. Elements in group 16 tend to form 2 single bonds. Elements in group 15 form 3. Elements in group 14 tend to form 4 single bonds. So keep in mind that 2 single bonds could be a double bond, or 3 single bonds could be a triple bond. Those are possibilities. So let's look at a couple more examples. Let's talk about H2o water. So the first thing we want to do is predict the location of the atoms. Remember, hydrogen is weird. It has to be on the outside just because it's so small. So it is to the left of the periodic table. It is listed first in the formula, but hydrogen has to be on the outside. And so we're looking at an arrangement of something like this. So count up the valence electrons. Oxygen will have 6, and there's only 1 oxygen, so there's 6 electrons. Hydrogen each has 1, and there are 2 hydrogens, so there's 2, and that makes 8 valence electrons, or dividing that by 2, we have 4 pairs that we can work with. Now that we've identified how many pairs we have, we can go ahead and draw single bonds between each of these atoms, and we'll subtract that out. And that tells me I have 2 pairs left. And these are most likely going to be lone pairs. So we look at the hydrogens. We can't put it on this hydrogen because its octet rule is complete. Same thing with the other hydrogen, its octet rule is complete. So we'll assign both of these pairs to oxygen in the middle. There's 1 pair. There's 2 pairs. And now we check to see, does oxygen obey the octet rule? 2, 4, 6, 8. And this is a possible Lewis structure for water. Now this one is valid. A lot of times though in textbooks you will see water that looks like this. This is a better indicator of the shape of water. The water molecule is bent like this to a certain degree, and this explains a lot of the chemical behaviors of water, such as why does it get bigger when it freezes versus this other one doesn't really tell us anything about shape or chemical behavior. But either one of these are valid, either one of these are perfectly fine if you were to find it on paper. Next up is CBr4. So as we saw on page 1, carbon, which is in group 14, probably forms 4 bonds. Bromine is in group 17, probably only forms one bond. So when we predict the location, carbon is to the left side of the periodic table compared to bromine, so it's probably in the middle. It also comes first in the formula, so those two things together tells me that it's probably a carbon surrounded by 4 bromines. So we need to count up the valence electrons. Carbon will have 4 valence electrons, only 1 carbon. Bromine is in group 17. There's 7 valence electrons, and there are 4 of them. There's 28. That makes for 32 valence electrons to work with. Dividing that by 2 tells us 16 pairs. Now that we know pairs, we'll go ahead and draw our single bonds, connecting all of the bromines to the carbon. Subtract that from our total. Tells us we have 12 pairs left to work with, and these are probably going to be lone pairs. So we're going to check all the bromines. So this bromine on the left appears to only have 2 electrons. To obey the octet rule, bromine has to have 8. So we'll add 3 pairs. That gives it 8 valence electrons. And I'll update my count. Same thing for the bromine at the bottom of the picture. It needs to have 3 lone pairs to obey the octet rule. The one on the right, same thing. And the one at the top also needs 3 pairs. And so that accounts for all of our electrons. All the bromines satisfy the octet rule. And the last step is for us to check if carbon obeys the octet rule. And so 1, 2, 3, 4 bonds. That's what we expected. That's 2, 4, 6, 8 electrons. And carbon obeys the octet rule in this particular Lewis structure.